the flat plate boundary layer. The classic and the most often used solution of boundary layer theory is for flat plate flow, which is also shown in this picture, which can be represented earlier laminar or turbulent flow in the previous video. In the case of laminar flow, for laminar flow past the plate, the boundary layer equation can be solved exactly for u and v, assuming that the free stream velocity u is constant, and we have this relation du on dx equals to 0. The solution was given by Prandtl, which was a student of Blasius in the early 20th century, dissertation from some experimental and with an ingenious coordinate transformation. Blasius showed that the dimensionless velocity profile d on u on dimensionless velocity profile is a function only of the single composite dimensionless variable. Let me write. So now we can have a definition eta. U on eta equals to u, the dimensionless velocity, f prime eta, and eta equals where the prime denotes differentiation with respect to eta, substitution to the of this equation to the boundary layer equation, which was for x and y direction. For example, we had this relation for the equation for boundary layer introduced before. As for continuity, we had this relation, and for the momentum we have this relation for pressure, which obtained as a function of free stream velocity. this case equals to 0, and the shear stress forces reduces to a, with some after much algebra, to a single third order nonlinear ordinary differential equation. Equation which is f triple plus 2f f7 equals to 0. Let me write at the first of the next page the equation where we have u on u equals to f prime eta, and eta is the non-dimensionless distance. The boundary conditions are at and at ten to 1. This is the Blasius equation. You write for which accurate solutions have been obtained only by numerical integration. Some tabulate values of the velocity profile are available. Velocity profile which was a function of eta are given in table 7.1 at the 7th edition. Frank and White. Since the velocity function u on u approaches to 1 as it is customary to select the boundary thickness delta as that point where, so in this case we choose delta, which is the where and the quantity near the unique for the limitation of the singularity. From the table, this occurs at approximately eta equals to 5 for the flow in a flat plate. On a flat plate. And we, in this case, u on u so now we can write an expression for the delta and Reynolds number from previous, we can obtain this relation. We choose delta where we should choose delta where u on u equals to the digit near the unique to avoid the singularity and the limitation. And also we, in this case for flat plate, eta is equal to 5. From the relation to eta we had this relation, eta equals to y u on nu x. So we can have this relation delta 29% as y and u on nu x 1 second as power. At the end we can reach to the Blasius equation for flat plate and the thickness of the boundary layer Reynolds x 1 second the Blasius equation. Table 7.1 the Blasius velocity profile provide values tabulated data about the 9-dimensionless velocity and the eta quantity. There should be also some software program to reach this data. With the profile now, Blasius of course could also compute the wall shear and the displacement thickness. The wall shear coefficient can be calculated as from the Blasius relation on displacement thickness delta star displacement thickness and the friction force shear wall coefficient. Notice how close these are to our integral estimated in the previous videos. When CF is converted to dimensional form, we have this relation for the shear stress as a function of x on wall the wall shear drops off with. You can interpret the relation the wall shear drop with 1 second power of the distance because of the boundary layer draw and varies as a velocity to the 1.15 power. This is the constant to laminar pipe flow where the For laminar we had this relation. Tau was proportional to the upstream velocity and is independent of that to x. If the wall shear stress to tau x substituted to the equation of the drag force, which was we had this equation for drag. Example 2 delta tau dx. In this case we have from 0 to the noun x, for example, we can make an integration for our previous relation for tau x, which was so we can calculate dx equals to this relation. The drag increases only as the square root of the plate length, this part of equation, increase with the square root of the plate length. The non-dimensional drag coefficient is defined as, so we can obtain non-dimensional, dimensionless or non-dimensional drag CD equals this relation 2D multiplied to the L rho U square BL. And is equals to the twice as the friction coefficient is the shear small shear stress coefficient at distance L, the drag coefficient, and for a flat plate from the Blasius relation. Thus, for laminar plate flow, CD equals to the drag force equals twice the value of the mean friction coefficient at the trailing edge. This is the drag on one side of the plate. Karman pointed out that the drag could also be computed from the momentum relation as stated before in dimensionless form, and we can calculate from Karman CD which from the previous definition, it can be right with the momentum thickness, which was theta x or theta delta. In this case, the drag computation of theta from the profile or from CD, the drag, so we can obtain the relation between the angular momentum thickness, and Reynolds. Delta on theta since delta is so ill-defined, the momentum thickness being definite is often used to correlate data taken from a variety of boundary layers under differing conditions. The ratio of displacement to momentum thickness, called the dimensionless profile shape factor, H equals to delta star on theta let me write in next page the dimensionless profile shape factor. Equals to H delta star on theta a large shape factor then implies that the boundary layer separation is about to occur. Large shape factor implies that boundary layer separation is about to occur. Separation if we plot the Blasius velocity profile from the relation in the form of the dimensionless velocity, which is function of velocity on the velocity of the upstream versus the dimensionless phi variable, we can see why the simple integral theory guesses. This figure shows the simple parabolic approximation of the Blasius velocity profile. The simple parabolic approximation is not far from the true Blasius profile, hence its momentum thickness is within 10% of the true value. Also shown in this picture are three typical two-gram flat plate velocity profiles, as shown for the values exact, Blasius profile parabolic, and the seventh root profile for various Reynolds number are available for turbulent flow. Notice how strikingly different in shape they are from the laminar profiles. Instead of the decreasingly parabolically to zero, the turbulent profile are very flat and then drop off sharply at the wall as shown. This picture is this point from the two walls. As you may guess, they follow the logarithmic law shape and thus can be analyzed by momentum integral theory if this shape is properly represented. Transition to turbulent. The laminar flat plate for flat plate. The laminar flat plate boundary layer eventually becomes turbulent, but there is no unique value for this change to occur. Picturing polishing the wall and keeping the free stream quiet, one can be delay the transition Reynolds number is Reynolds X transition from laminar to flow 5 multiplied to 10 power 5. However, for typical commercial surface and velocity free stream air is valuable, but there is another condition also for Reynolds transition, that is 3. This is the end of this section. The next section is turbulent flow approximation on a flat plate.